Welcome everyone to this lecture on big science collaborations. My name is Niels Martens and I am a philosopher of science and a physicist interested in big science and big science collaborations. I used to be part of a large interdisciplinary research unit on the LHC, the Large Hadron Collider, both the physics and the collaborations. And nowadays I'm an active member of the NGEHT, the Next Generation Event Horizon Telescope collaboration. More on that later. So what I want to talk about today is the era of big science that we're in. And collaborations in physics, astronomy, other sciences can be big in a multiplicity of ways. For instance, physically, either because the instrument is very large or because its parts are spread very far apart. Or it can be because the members of the collaboration are dispersed, often around the whole globe. Collaborations can also be big in the sense of being very costly financially, in terms of the human resources involved, and often this means we need contributors from many different communities, whether that's engineers, telescope operators, physicists, computer scientists, etc., etc., etc. And finally, often these collaborations are also large in the sense of temporally, in that planning, operating can take years or sometimes even decades. So let me illustrate this with a few examples. Starting with the Event Horizon Telescope collaboration. This is a collaboration that makes images of black holes, as you might be familiar with. And what they did is borrow existing telescopes across 6 sites all across the globe, and that's why it's relatively cheap, and put that data together to, in the supercomputer, reconstruct one virtual telescope the size of the Earth. So physically speaking, it's quite a large collaboration. And then we have the Next Generation EHT, which I'm a part of, which tries to improve the resolution and make high-quality videos of black holes by building additional 10 telescopes in all different sites across the world, such as, for instance, Kilimanjaro. So the size will be the same, but yeah, the price tag is a bit more. And scientists are, of course, always thinking ahead. So the next thing on the wish list would be to extend the baseline, include one that reaches into space by including a satellite, such that we have a virtual telescope that's even bigger than our own planet. But yeah, this also has a larger price tag. A few more examples. LISA, space-based gravitational wave detector, is probably the biggest one in terms of physical size, because the arms will be 2.5 million kilometers long, is the plan. And then we have, of course, famously the collaborations associated with the Large Hadron Collider. I mean, different people will tell you different numbers. Depends on how you count how many scientists are involved. But either way, this is definitely the example with the highest number of people involved. And then we also have the ground-based gravitational wave detectors with also quite a few scientists involved. So we have seen some examples of big science collaborations which can be big in different ways, and often they're big in many ways at the same time. And this has a few consequences for a few aspects of big science that arise as a result. So one thing is that in many of these cases we have unique experiments, right? We have to spend all the money or used up all the people involved to create that one experiment, or maybe it's on a very unique location, such that we cannot build another one. Whereas we, of course, tend to think the strength of science is that repeatability, that we often have multiple independent experiments converging ideally at the same result. So that can be a challenge here. Another aspect is that often things can get quite political. On the one hand, internationally speaking, because a lot of funding is often required from different countries, and people from different countries are involved, but also internally. These collaborations can get so big, there's a lot of hierarchical structure often, sometimes egos involved, power, so internal politics can also play an important role there. The third aspect is what philosophers like to call social epistemology, which is the fancy word for just how knowledge is created in large groups. So depending on how you structure your group, psychological and sociological effects, this might all influence the final result. And then finally, these groups often by necessity are very interdisciplinary, need to bring together engineers, computer scientists, mathematical physicists, sometimes lawyers, etc., etc. And these people operate in different ways, so that can lead to cultural interdisciplinary barriers that one needs to be aware of. And so let me illustrate some of these aspects on the next few slides. I think the first thing I'd like to say is that I think the Nobel Prize personally doesn't nowadays really reflect this era of big science, in that it really still portrays individualistic science and is in that sense a bit outdated, and perhaps at this point it does more harm than good. Here's some more examples, all different in their own way. One infamous example is the 30-meter telescope. Right, so these are all examples of why just focusing on the physics is not going to cut it. There's often much more involved. So Mauna Kea, the 30-meter telescope, in terms of physics, finances, everything was set, but as often happens in the history of astronomy, local communities were basically ignored, not involved, not engaged with, and for them, Mauna Kea, the volcano, has a lot of spiritual value, and they didn't want another telescope on top of there, so they protested and delayed the project for years. Then we have the super collider, SSC, totally different example. This was in the 80s and the 90s in Texas, and this was supposed to be a collider even bigger than the LHC. And it was well on its way, but there were lots of debate in US Congress, lots of politicians involved who were skeptical that the money was really best spent on something like this. And then the project started costing more and more money, management wasn't great, and eventually the project had to be halted, even though already 20 kilometers of cave was dug and $2 billion spent. And of course, this raises the question, especially in the context of particle physics, what's next? Are we going to have an even bigger collider, such as the future circular collider? On the one hand, it's not necessary that we're going to find new physics, like the case for the Higgs boson before 2012. There might not be any new physics up to the Planck scale. On the other hand, if you would stop building colliders and lose a whole generation of particle physicists, then there's of course a lot of tacit knowledge that disappears in that sense. And another aspect of these big science collaborations is that a lot of large-scale coordination is involved. So for instance, how this happens in astronomy and astrophysics, that there's a decadal survey. Every decade, the community comes together, lots of workshop, lots of coordination to produce a report, which then can be used by politicians, funding agencies, to relatively quickly understand what the community as a whole wants to emphasize for the next, say, 10 years. And for instance, in particle physics, there's a lot of there's also a similar report, but more frequent than every 10 years, where, for instance, all the European particle physicists come together, lots of committees, lots of deliberation, takes years to then discuss what they think the focus points should be within particle physics for the next few years. On this slide, I would like to illustrate or give an example of how complex, organizationally speaking, some of these collaborations can be, much more complex than a local research group. So for instance, here we have CERN and the associated collaborations, right? The European Center for Nuclear Research, which is responsible for the Large Hadron Collider. Now, it's not like CERN is its own country, right? It's located in France and Switzerland, but nonetheless, to some extent nowadays, it's legally independent in some aspects, for instance, in terms of taxes and to some extent diplomatic immunity. But what you don't want to happen is that those two countries can determine who gets a visa, who is allowed to come into CERN, etc. Right? There are all these different countries involved, and they all need to have equal rights. Then we have a CERN Council, where all the different member states have a number of delegates and a vote. So democratic aspects come into play. And also the CERN itself is officially an observer at the UN General Assembly. Now you might have thought that, okay, all the detectors, the experiments, Atlas, CMS, etc., fall under CERN in terms of the organizational structure. That's not the case. They are independent entities. They make their own decisions. And yes, they have CERN as one of the members, but there are many other members. And CERN does provide some of the funds, but definitely not all of the funds. So yeah, they are their own entity. And often they are characterized by a vast number of committees. Right? So if you want to write a paper, there's so many steps of internal review, so many people get involved. If you want to go to a conference, you cannot just go to a conference or give a talk at a conference. This all goes via various committees. So this is just to give you a taste of how complex such structures can get, as you see here. So what I tend to find helpful when looking at these big science collaborations is to place them along this one-dimensional axis. So what we see here is a spectrum of what you might call very top-down collaborations in terms of how they are structured and how that affects the knowledge that eventually comes out of a collaboration. And on the other extreme, we have more what I'd like to call bottom-up collaborations, groups, entities, right? So some examples of paradigmatic top-down collaboration is, for instance, the collaborations such as Atlas that are connected to the Large Hadron Collider. And at the other end of the spectrum, we see just like whole scientific communities or maybe entities such as the Intergovernmental Panel for Climate Change. So let me illustrate what I mean by these examples. So what we typically see for top-down big science collaborations is that all the people involved work in the same place, one big physical headquarters or just a few, a centralized funding stream, and often the collaboration has just one or a few purposes, like detecting the Higgs boson. That often means that the collaboration tends to get prioritized over the individual member. And the aim is often to produce some consensus result, and this can sometimes mean that diversity of opinions isn't always valued as much as perhaps it should. And often these collaborations can become quite hierarchical, such as, for instance, in the case of Atlas, you have loads of now committees which make loads of decisions. If you want to publish a paper, there's so many internal review steps. If you want to, as I said, go to a conference, there's so many, right? Nothing is determined by one individual member. On the other hand, if you look at whole scientific communities or entities like the IPCC, there it's kind of the other way around. So there's not one place where all the scientists meet, but communication is kind of in a much more loose, dispersed way via conferences, publications, etc. That's how knowledge gets exchanged. Right? Authors coalesce in and out of projects. They change who they work with. This, of course, means that individual scientists have much more freedom to pursue what they want to pursue. Of course, that means they will have to get the funding for that themselves. And then here it's much more okay if different groups publish different results, which might be contradicting each other. And then maybe at some stage with meta-analyses or something like that, the knowledge gets brought together, but that's then at a much later stage. Right, so all of these extremes, each of these extremes has some benefits and some drawbacks. So the top-down collaborations tend to be quite good at really focusing on a few purposes and being very effective at achieving this. And also, especially if lots of funding is required, this is perhaps one of the only ways to go. I'll say more about consensus later. But as I said, if you're an individual member in a collaboration, especially if you're not at the top of the food chain, then it can often feel like you're just a cog in the wheel, where there's less room sometimes. There's a risk that there's less room for individual creativity. Carving out an individual PhD project tends to be difficult if all the papers you write are with 3,000 other authors, especially if you're at a university where you can't use anything in your PhD, which is written with other people. And also, how to give credit if every result is created by thousands of people. And in the bottom-up cases, it's kind of the other way around. It's more difficult to have grand achievements, coordinated achievements, if everyone kind of does their own thing. On the other hand, for an individual, there tends to be more freedom And if you do something and you publish a paper by yourself and a small group of people, then it's clear that you have done the work. And if there's credit to be given, you deserve that credit. And so what we're trying to do with the NGHT collaboration is to be somewhere in the middle here in the sense of being the best of both worlds. So what I want to do in the remaining slides is focus on the NGHT as a case study, because I know that collaboration best, but also because it's a new collaboration, we're setting it up. So this is exactly the time where we have lots of room to make these decisions in an explicit way rather than building upon decades of already pre-existing collaboration structure. Nonetheless, much of what I'll say in the next few slides will apply in one form or another to many other big science collaborations. So the NGEHT has 11 working groups, 3 engineering working groups, 8 science working groups. And one of those science working groups is the History, Philosophy, Culture working group, which I'm part of together with 50 very active scholars from the social sciences and the humanities. What we're trying to do is improve the collaboration, and we do that according to 4 focus areas. So let me just briefly go through them one by one. One is responsible telescope sighting, or building a telescope somewhere. Basically what we want to do here is not what happened at Mauna Kea, but rather from the very get-go, identify stakeholders locally, engage with them, ask what they would want, what would be a mutually beneficial situation, and accept that a no might just be a possible answer you get if you want to build a telescope there. Another focus group focuses on foundations. Right, often the mathematicians come with very formal, neat, idealized results. And then the reality that the experimentalists, etc., have to deal with is much more messy. So how do you bridge that gap? That's some of the topics we work on. A third focus group has 2 parts. So let me go through them. First, algorithms and inferences. Often in these collaborations, lots of computer scientists, algorithms, simulations are needed, like at CERN, simulations of how the detector works, how you calibrate the detector, and in the case of black hole imaging, algorithms that actually, in the end, produce the image. And this is often done by many different people involved, often different generations. Code is not always documented very well, so that can lead to parts of the code working, but you don't really know why. Might just be some artifact, parameters where not everyone knows what their role really is, etc., etc. So you need to be careful on. You need to think of how to mitigate these results where you're not just writing code by yourself, but with different groups and maybe even different generations of people. Second part of that focus group focuses on visualization, right? The image that's eventually produced. Many decision points here, which you might not have really thought of. Well, in astronomy, often when you're not imaging in optical range, there's no obvious color. You have to choose which color when you want to produce an image. And as physicists, we know, right? So this is the accretion disk, plasma very hot. And as physicists, we know, well, blue is actually much hotter than these colors. Nonetheless, for the person on the street, this tends to be more of a warm, hot color. So they've chosen here, nonetheless, to go for this color, even though as a physicist, you might have chosen a different color. Another decision point, they're going to make one image for the scientist and one for the public. The HT has decided not to do this, just one image for everyone. And more recently, there's a new image from a different collaboration involving the Greenland telescope. And there, they decided in Nature to have something quite similar to this. But then the press agencies were like, no, we're going to use purple and a different kind of image, right? So there are different choices to be made here. And one thing I would like to highlight is the work of Elizabeth Kessler, who looks at the images of the Hubble Space Telescope. And there she points out that these color schemes are inspired by, very similar to paintings, especially patriotic paintings in the American West. So the point is there that these decisions are always part of a broader visual culture and are influenced by it. It's very interesting to look into what eventually determines which color is chosen and how that influences how the public sees the results and understands the results. Okay, and then now moving on to the fourth focus group, how to organize your collaboration and what influence this has on the eventual output, whilst at the same time also not only optimizing collaboration as a whole, but also optimizing the welfare of the individual members. So that's what we're trying to do here for the NGHT collaboration. And basically, we need to work simultaneously at multiple fronts. They're all connected and related, but I'll nevertheless go through them one by one. So first thing that's very important is to get a feel and understanding of how communication works within a collaboration, right? Then you know where the decisions are made, how hierarchical or egalitarian collaboration is, and what influences the eventual outcomes. There's lots of tools from network analysis. Digital humanities can be used if you have the right data. For Atlas, for instance, it's quite easy because there are 175 mailing lists, so you can easily represent that and analyze that. For the NGHT, it's much more challenging because much of the communication happens much more via individual emails, etc. So it's more difficult to get data to understand this. And this is the data we need to then feed in all to these other aspects we're looking into. For instance, one thing you need to think of when starting collaboration is what is membership, how to define membership, who can be a member of the collaboration, especially if that means you're also on the general author list, right? Because many people get frustrated if so all of a sudden, just before a big publication, oh, we have 500 new members who then get added to the author list and credit gets watered down. So it's important to define what it means to be a member. For instance, that the LHC often need to do a qualifying task every so often to remain a member, so you really need to do something for it. And then it's important to develop something like a code of conduct, ensure that it reflects the situations of all the communities involved. And what's tricky here is, of course, that there's no one HR department for the collaboration, right? Everyone is at their own local institutions with their own HR department. So it's hard to think about what to do if the code of conduct is violated. And of course, you want to make sure that it really reflects, that it is tailored to all the specific communities involved in the collaboration. And of course, you want to keep updating it. So one way of doing that is that every so often you have an internal survey about the climate, the atmosphere, possible challenges, and use that to update the policies in place. So membership, that's one topic. Another topic or technique that's becoming quite popular in recent years is called expert forecasting, or forecasting tournaments, which are very subtle ways of extracting from the members what they think the possible outcomes of the collaboration are and how likely they are. For instance, you can do that with like an online market system where people can buy bets, sell bets based on possible outcomes. Why is this important? Because, well, you need to make tough decisions when designing your instrument or your telescope array. You have limited resources, and if you have a good understanding of how likely you think every outcome is and what you need to do to even look into that observable, etc., then it's good to have an understanding of all these likelihoods. Because one of the first things you do as a collaboration is come up with all your science goals and then prioritize them in something called a key science goals document. That often includes an STM, a science traceability matrix, where you have all these goals and you figure out which are most important, most likely, and what does that mean for like which frequencies should we observe with, where should we place the telescopes, etc. And this then also leads us to better understand how hypotheses are generated and tested in such a collaboration. And also, once you finally get results, which sometimes can be like years after you started the project, how novel they are. You might think, well, that's obvious, but often history gets rewritten. Now we tend to think, well, the Higgs boson was inevitable that we were going to find it. But actually, well, interviews with physicists before 2012 sketch a totally different story. So it's interesting to keep track of these predictions and how they change over time to better understand the scientific process, especially in such a complex, large group. And then, another topic in the end on governance, how do you structure collaboration? There are many different options. And one thing we're trying to focus on with the NGHT is to advise that there should be a scientific council with elected members, such that all the different stakeholders geographically, but also junior members are represented and have a say. And then finally, there are two related topics, authorship and consensus and diversity of opinion, where authorship is all about, well, how do you go about writing a paper with hundreds of people or thousands of people even? And this is about, well, how not everyone is going to agree. How do you approach that? How do you make use of the value of the diverse opinions? But that's what we'll discuss in part 2 of this lecture. For now, I want to summarize. What I've tried to show is that we're in the era of big science, and that can mean multiple things. Often collaborations are big in many ways. This means that things can get political, group dynamics, sociological, psychological effects can become important, and there are barriers between the different disciplines and cultures involved that can provide challenges. And so I would contend that if you want to do the best possible thing in such a collaboration, that you should try to get all the help you can find, which include expertise from all areas of STEM, but also beyond STEM, the social sciences and the humanities, to optimize the whole process. Thank you for your attention, and see you back for part 2 of this lecture.